Limits at infinity use the symbols x approaches positive infinity and x approaches negative infinity to denote that x is increasing or decreasing without bound. These are just symbols that we use to indicate the non-stop increasing or decreasing behavior of the independent variable x. Take note that when evaluating the limit of a quotient at infinity, first divide both numerator and denominator by the highest power of the variable appearing in the denominator. Also take note of this theorem. Let r be any positive integer, then, letter A, the limit of 1 over x raised to r as x approaches positive infinity is equal to 0, while the limit of 1 over x raised to r as x approaches negative infinity is also equal to 0. Let us have an examples. Number 1. Find the limit of 1 over x raised to 6 as x approaches positive infinity. According to this theorem, the limit of this function is 0. Number 2. To find the limit of 12 over x raised to 15 as x approaches positive infinity, we can rewrite the function as limit of 12 times 1 over x raised to 15 as x approaches positive infinity, then simplify. Limit of a constant is the constant, so this is 12, and the limit of this is 0 by applying this theorem. Thus, 12 times 0 is 0. For number 3, find the limit of 2x plus 3 over 4 minus x as x approaches positive infinity. To find the limit of this function as x approaches positive infinity, we first divide both numerator and denominator by the highest power of the variable appearing in the denominator. In this case, the highest power of the variable in the denominator is x. Thus, we divide each term in the numerator and denominator by x. So we have limit as x approaches positive infinity of 2x over x plus 3 over x divided by 4 over x minus x divide x. Then simplify. 2x divide x is 2 plus 3 divide x is 3 over x over 4 divide x is also 4 over x minus x divide x is 1. Next is to now find the limit of each term. The limit of 2 as x approaches positive infinity is 2, limit of a constant, plus the limit of 3 over x is 0. We use this theorem. The limit of 1 or any number divided by x raised to r as x approaches either positive infinity or negative infinity is always equal to 0. Then, the limit of 4 over x is also 0 using this theorem, minus the limit of 1, which is 1, limit of a constant. Thus, 2 plus 0 is 2, while 0 minus 1 is negative 1, and 2 divided negative 1 is equal to negative 2, and this is the limit of this function. Number 4, find the limit as x approaches negative infinity of x squared plus 2x plus 1 over x cubed plus 4. Same process. First, divide the numerator and the denominator by the highest power in the denominator. In this case, x raised to 3. So divide each term by x raised to 3 and then simplify. X squared divided x cubed is 1 over x. We crossed out x squared in the numerator and in the denominator. But since we have x cubed in here, we still have 1x left in the denominator. Plus, 2x divided x cubed is 2 over x squared. We eliminate x in the numerator and subtract 1x in the denominator. Plus, 1 divided x cubed is 1 over x raised to 3. Over x raised to 3 divided x raised to 3 is 1. Plus, 4 divided x cubed is 4 over x cubed. Next, find the limit of each term. The limit of 1 over x is 0 from our theorem. Just take note that if we are looking for the limit as x approaches positive infinity or negative infinity of 1 or any number over x or x raised to any number, the limit is 0. Then the limit of 2 over x squared is also 0. Limit of 1 over x cubed is also equal to 0. Over the limit of 1 is 1, limit of a constant, plus the limit of 4 over x cubed is 0. So 0 plus 0 plus 0 is equal to 0. Over 1 plus 0 is 1. And 0 divided 1 is 0. And this is the limit of this function. Number 5. Find the limit of x over square root of x squared minus 1 as x approaches positive infinity. The highest variable in the denominator is square root of x squared. Take note that we have a radical symbol in the denominator, so we have to divide the numerator and denominator by square root of x squared. Here, instead of writing square root of x squared in each term, we can just expand the radical symbol and divide each term inside by x squared. In the numerator, we divide this by square root of x squared or just x. Why x? Take note that square root of x squared, when simplified, is equal to x. That is why we divide the numerator by x, because square root of x squared is just equal to x. Next is to simplify each term. X divided x is 1. X squared divided x squared is also 1. Minus 1 divided x squared is 1 over x squared. Then, find the limit of each term. Limit of 1 as x approaches positive infinity is 1, limit of a constant. Here, the limit is also equal to 1. Minus, the limit of 1 over x squared is 0. Copy 1, then 1 minus 0 is 1, and square root of 1 is 1. Thus, 1 divided 1 is 1, which is now the limit of this function. Then we have theorem number 2, limits at infinity of polynomials. Letter A, the limit of x raised to r as x approaches positive infinity is equal to positive infinity. B, the limit of x raised to r as x approaches negative infinity is equal to positive infinity when r is even, and it is negative infinity when r is odd. Examples. Number 1. Find the limit as x approaches negative infinity of x raised to 4 plus 1 divided by x squared plus 3x. Since x approaches negative infinity, this is limit at infinity, we do the same process. First, divide the numerator and denominator by the highest variable appearing in the denominator. In this case, we have x squared. So we divide each term by x squared, then simplify. X raised to 4 divided x raised to 2 is x squared, plus 1 divided x squared is 1 over x squared, over x squared divided x squared is 1, plus 3x divided x squared is 3 over x. Then, find the limit of each term. Since x approaches negative infinity, we use this theorem. If r is even, the limit is positive infinity, and if r is odd, the limit is negative infinity. Since r is 2, which is an even number, the limit of this term is equal to positive infinity, plus the limit of 1 over x squared is 0, using the previous theorem, over limit of 1 is 1, limit of a constant, plus limit of 3 over x is 0. Positive infinity plus 0 is equal to positive infinity, over 1 plus 0 is 1, and positive infinity divided 1 is positive infinity. Therefore, the limit of x squared plus 1 over x squared plus 3x as x approaches negative infinity is positive infinity. Number 2. Find the limit as x approaches positive infinity of negative 6x raised to 5 plus 3x squared minus 2. Since the given is a polynomial function and we are evaluating the limit as x approaches positive infinity, we need to factor out the highest variable in the given function. In this case, we should factor out x raised to 5. And this will become limit as x approaches positive infinity of x raised to 5 times negative 6 plus 3 over x cubed minus 2 over x raised to 5. X raised to 5 times negative 6 is equal to negative 6x raised to 5, which is the first term in the given function. X raised to 5 times 3 over x cubed is equal to 3x squared, the second term. Take note that x raised to 5 times 3 over x cubed is equal to 3x raised to 5 over x cubed. Simplify the variable x raised to 5 over x cubed. This will be equal to x squared. 5 minus 3 is 2. Thus, we have 3x squared. And x raised to 5 times negative 2 over x raised to 5 is negative 2. X raised to 5 times negative 2 over x raised to 5 is equal to negative 2x raised to 5 divided by x raised to 5. Cancel out x raised to 5, we have negative 2. After this, we now find the limit. Limit of x raised to 5 as x approaches positive infinity is positive infinity. Theorem number 2. Limit as x approaches positive infinity of x raised to r is equal to positive infinity. Next, limit of negative 6 as x approaches positive infinity is negative 6, limit of a constant, plus limit of 3 over x cubed is 0, minus limit of 2 over x raised to 5 is also 0. Copy positive infinity, negative 6 plus 0 minus 0 is equal to 6, or negative 6. And positive infinity times negative 6 is equal to negative infinity. When multiplying an infinity and a number, the answer is infinity. We just need to multiply the signs of the given function. Thus, positive times negative is negative. So the limit of this function as x approaches positive infinity is negative infinity. And that is all about limits at infinity.